Um, Now we're back to section 5.7, and this time we're discussing the substitution method for definite intervals. What we've done so far is the substitution method for indefinite interval. And I want to remind you the first example that we did. We did the indefinite interval of 3e to the power 3x dx. We assumed u to be 3x, du to be 3dx, and we figured out the integral becomes e to the u du, and then the antiderivative is e to the u plus c, and then by replacing back I get e to the power 3x plus c. So how do I deal with when there are bounds in here, when it's definite integral from 1 to 2? One method of doing this is to go all the way, ignore the bounds, and find the antiderivative, then use the fundamental theorem and say, okay, so antiderivative is e to the power 3x, and then I plug in 1 and 2. And so I get e to the power 6 minus e to the power 3, right? 2 times 3, 6, and 1 times 3, 3. So that's one method. It requires you to completely do the definite integral, then do the indefinite integral. Here's another method though, however. So the other method, finding a u and du is the same. So I look at this integral and I say, so u has to be 3x, du has to be 3dx, and then instead of just stopping there, you do one more step. For x equal to 2 and x equal to 1, which are the bounds, you find u. For x equal to 2, plug it into here and you get 6. For x equal to 1, plug it into here and you get 3. So when you do this, then you change your integral. Instead of finding just the antiderivative and then using the fundamental theorem, you find the substitution, you find the bounds, then you use the fundamental theorem. So this becomes x equal to 1 down here should become 3, x equal to 2 up there should become 6. What we have is 3dx should be du, and e to the power 3x should be e to the power u. So now I just, like any old integral, I solve it. E to the power u is the antiderivative, and 3 and 6. So I get e to the power 6, e to the power 3. So sometimes, and people sometimes ask which way is better or which way is the worst. And as you go, sometimes you see there's benefit to do it this way, or there's benefit to do it that way. Algebraically, I mean, one way or another make your life a little tiny bit less algebra involved, and so that's what you pick. But you want to learn both methods, even though either method would work in any examples that we do for a long time. You just want to make sure that you know both methods, because eventually at some point you see that one makes your life a lot less complicated than the other one. And so that's that. And let's go to the next example. So one thing before the next example, we want to make sure that this is understood. When you're taking the antiderivative of f of g of x, g prime of x dx, then through substitution method, the integrand and the differential become f of u du. So what happens to a and b A becomes G of A and B becomes G of B. That's because we have to plug it into the whatever function that you're assuming to be U. Now, example, integral from -1 to 4 of 2 times 5 minus 3x to the power 2 dx. If you remember from the beginning of the integral, I could have foiled this thing and find the antiderivative. But now that we're much more sophisticated, I'd rather do a U substitution. So what's the complicated part? That. And so I use U to be 5 minus 3x, then du is going to be -3 dx, and so dx is -1/3 of du. And over here, everything's, when I see that's the part with the antiderivative, I have to figure out for x equal to 4 and x equal to -1, x equal to 4, if I plug it into there, I get 5 minus 12, u equal to 5 minus 12, which is -7. If I plug in x equal to -1 in there, I get 5 minus 3, which is 5 plus 3, and that is 8. And so this integral becomes, see, the bottom becomes, and bottom bound is 8, the top bound is 7, the function, the integrand is 2u to power 2, and dx is going to be -1/3 du. And so you multiply things through, and negative sign changes the order. See, I changed the order, I used that a negative. The upper and lower bound. And then 2/3 came out, u to the power 2 du. And that is 2/3 u to the power 3 divided by 3, -7 and 8. And that is 2 divided by 9, 8 to power 3 minus 7 to power 3, which is 2/9 of 8 to power 3 plus 7 to power 3. Let's do another example. Let's evaluate integral from 0 to 1 of the third root of 1 plus 7x. First thing first, I feel like u should be 1 plus 7x. And then du is going to be 7 dx. And then for x equal to 1, x equal to 0, plug back in. And x equal to 1 over here gives me 7 plus 1, 8. X equal to 0 gives me u equal to 7 times 0, which is 0, 1, plus 1 and 1. So the integral becomes 0, 1 to 8. And so over here I need to solve for dx. dx is 1 over 7 du. And in here I get u to power 1/3 and 1 over 7 du. 1 over 7 comes out, 1 to 8, u to power 1/3 du, and that is 1 over 7, u to power 4/3 times 3/4 plus, and from 1 to 8. And so simplify, clean it up. And u, which is 8 to power 4/3 minus 1 to power 4/3. That's 3 divided by 28. 8 to power 1/3 is 2. 2 to power 4 is 16. 1 to power 1/3 is 1. 1 to power 4 is 1. So what you end up is 328 times 15 and you can clean it up and get 45 divided by 28. And so that's another question. I clear question 7. Consider the definite interval from 1 to 5 of 2x over x squared plus 1 to power 2 dx. And following, if you use substitution, which of the following is going to be equivalent? So now that you paused and found the answer, let's go over this. I feel like u should be x squared plus 1, and du should be 2x dx, and then 5 and x equal to 5 and x equal to 1 are going to 5 to power 2 plus 1 is u equal to 26, and 1 to power 2 plus 1 u equal to 2. So the bound should be 2 and 26, and I have to have a u to power negative 2 and du. So C is the answer. So example 12, evaluate integral from 0 to 2 x to the third over x squared plus 1 dx. Again, in here I feel like denominator is something that I want to make it a little simpler. So I make u to be x squared plus 1. And then du is going to be 2x dx. I don't have a 2 in there, so I make 1/2 of du equal to x dx. Looking at that, I see that I have x to the third dx. So basically breaking this down is going to be 0 to 2 x squared over x squared plus 1 x dx. So far not too bad. What I can do in here is I have to figure out how to replace this, because the bottom becomes u. Well, what is x squared? And by solving right there, I get x squared is equal to u minus 1. The last piece is changing 2 and 0. So 2 plugging into here, I get 2 to the power 2, 4 plus 1, 5. Plugging 0, I get 1. So I get integral from 1 to 5 of u minus 1 over u, and then 1/2 of du. So not too bad right now, but how do I still have a quotient in here. What am I supposed to do? Here, remember, because the denominator was only one term, I can put each term in the numerator over that denominator, and that helps. So I get u over u minus 1 over u du, which is the 1/2 of integral 1 to 5 of 1 minus u to the power negative 1 du, and that is 1/2 of u minus natural log of u, 1 and 5. Plugging in 5, I get 5 minus natural log of 5, then minus 1/2, 1 minus natural log of 1, which is 0. And so 5/2 minus 1/2 will give me 4/2, which is 2, minus 1/2 of natural log of 5 is the answer. Okay. Now we're getting to the questions that basically, if it's completely, if the rule of the function is not known, how do I use the use substitution to compare two integrals. And so over here, we're comparing integral from 0 to 4 of f of x dx, which I know is 2, to integral from 0 to 2 of f of 2x dx. Oh, seems like I'm taking the integral. This one as a composition, that one is just a function by itself. If it's composition, then I may want to think about the chain rule, which is the antiderivative, and then it would be the u substitution. So let's see what u equal to 2x do for us. U equal to 2x is going to make du equal to 2 dx. And then and from here, what you get, I'm not completely done because, wait, 1/2 of du equal to dx. I have to change the bounds also to and 0. And then x equal to 2. Where's the u? U is right there. Makes u to be 4. X equal to 0 makes u to be 0. So this integral, the second integral, changes to integral from 0 to 4 of f of u times 1/2 d of u. Clean it up a little bit. It's 1/2 of integral 0 to 4 f of u du. Well, that's exactly the one that we started and we wanted to compute basically. And so basically it's 1/2 of 2, which is 1. And so in this specific case, again, when you're doing the integral and rule of the function is given, you can do either method for the definite integrals. But if the rule of the function is not given and you're just comparing, so when it's more of a comparison and more conceptual matters, then you have to know both methods to survive this type of questions. I click here question 8. Evaluate the definite integral from 9 to 10 of x square root of x minus 9 dx and using substitution. Now that you evaluated, let's evaluate together. Here again, I want u to be what's under the square root, x minus 9, and du gives me dx. 10 gives me x equal to 10 gives me u equal to 1, x equal to 9 gives me u equal to 0. So the integral becomes integral from 0 to 1. Here I still have x, so I have to solve for x. X is equal to 9 plus u, 9 plus u, square root of u du. Basically, distribute the square root of u, and you get 0 to 1, 9u to power 1/2 minus u to power 3/2 du, and this becomes 9u to power 3/2 divided by 3/2, which makes 9 divided by 3/2 means it's 9 times. It's 9 times 2/3, which is 3 times 2, which is 6. And then minus u to power 5/2 times 2/5 and 0 and 1. When you plug in 1, you end up with 6 minus 2/5. When you plug in 0, you get 0. Subtracting is 30 minus. Oh, I'm sorry. Here it was positive. So 30 plus 2 is 32 divided by 5. And that is C.